Hello everybody, and welcome to another episode of Back to Basics. Last week we learned about resistors in series and parallel, and this week we're going to learn about capacitors in series and parallel. Now, thankfully, it's pretty much the same thing, only switched around, which is why I reversed the colors here. So, let's get right to it. Now I'm going to reach into my bag here and pick, say 4 random capacitors. Hopefully they're sufficiently different. Alright, we have a 3.3 micro, and we have another 3.3 micro. I want something different. And then we have a 100 micro, and then we have another 100 micro. Let's grab something different. What about this yellow one? This one is a 0.22 micro. And then this one is a 47 micro. So we've got a couple of good different values here. And we'll play around with those in just a moment. So let's start with capacitors in series. So now I know I'm not drawing electrolytics here, even though I'm using electrolytics in the example, but we'll overlook that for the time being. So, let's start with this one. This one was what? 100 micro. 100 micro. And then this one is 3.3 micro. And then this one was 0.22 micro. And then this one was 47 micro. I should have left a little bit more room. Alrighty. So, if these were resistors, when we added them, or when we calculated the total capacitance here, we just added all together. But capacitors work the other way around from resistors. So these ones are going to require that annoying calculation that we did before. So the total capacitance is equal to big paren and then another paren 1 over 100 micro. Being as they're all in microfarads, we don't have to really distinguish like I would normally use exponential notation for this, but we'll just leave it with their discrete units and it'll be the same thing. We'll just remember that we're working with microfarads. Plus 1 over 3.3 plus 1 over 0.22 plus 1 over 47. And then all of that to the -1. So let's go ahead and whap that into our calculator. So 1 over 100 plus 1 over 3.3 plus 1 over 0.22 plus 1 over 47. Close both parens. Take that all to the -1. And we should see 0.204 microfarads. Now, that seems so low because the sum of all the capacitance in series will be less than the smallest capacitor in the group. Just like with resistors, when the sum of the resistors in parallel was less than the smallest resistor in the group, the sum of the capacitors in series is less than the smallest capacitor in the group. The smallest capacitor in the group we had was 0.22 microfarads. So let's go ahead and put these onto a breadboard and measure the capacitance. I've got to make sure I get the polarity correct here. Boy, these leads are just not conducive. Okay, we're going to trim these leads because they're making life difficult. Bear with me a moment here. Bunk. And one more. Bunk. I believe these capacitors are 20% tolerant, so there will be a fair bit of drift in our actual measurement, but it should be close enough to at least demonstrate the concept. So, let's go ahead and, these are kind of low quality breadboards. We'll plug that one in, and then this one, and then last but not, oops, I did this one backwards. And this one. There we go. Alright, and then we'll grab my multimeter here, and we'll set it to capacitance. I don't use this function very often on my meter. And we'll go ahead and clip this guy over here, and we'll clip this one over here, and get something completely erroneous. 76.6 nanofarads. We should be seeing 200 nanofarads. I wonder if one of these capacitors is bad. I've got them all. Oop. Now we've got 144.3 micro. Oh, something weird is going on. Bear with me a moment. I will be right back while I try to figure out why this isn't reading very well. So, after some troubleshooting, I realized that I was being really dumb. Sharp-eyed viewers will note that I set up the capacitors initially in parallel and not in series. So that was part of my problem. Another part of the problem was I don't think that multimeter is working too well for capacitance readings. Anyway, so I figured out what was going wrong, and I also found out that one of the capacitors was way out of spec, so I found some that were closer. So we put these all in series, and we calculated that it should be 0.204 microfarads, or 204 nanofarads. So if we run this capacitor checker, we get 178.7 nano, which is close enough, given that the capacitors aren't, exactly those values. So, now that that's all figured out, let's talk about doing them quickly in parallel. Now, that's a much easier proposition here. Well, let's start here. We'll just go like this. That's messy, but good enough. Alrighty, so we had 100 micro, a 0.22 micro, a 47 micro, and what was the other one? It was 3.3, I think. That's the 0.22. 47, 100, 3.3. I was right. And 3.3 micro. Now, in parallel, they all add, which explains the erroneous readings I was getting before. So we've got 100 plus 0.22 plus 47 plus 3.3. 2, 5, 10, 5, 1. So we should come up with about 150.52 microfarads when we put these in parallel. Let's see what happens. Make sure the polarities are correct. we'll grab the tester again and put the leads in the tester. So we should see around 150 micro when we start this tester. Let's see what we get. We get 146.8 micro, so that's fairly close. Anyway, that's pretty much it for capacitors in series and parallel. If I left anything out or made anything unclear, feel free to start a discussion in the comments below. If you haven't already, consider clicking here to subscribe. Right over here will be a video that YouTube thinks you'll find interesting based on your watching habits. Over here will be the Back to Basics playlist. And right here will be a link to my Patreon. Patreon subscribers do get these videos 1 week in advance. Thanks so much for watching, and we'll see you next time. Bye-bye.